Alright, so we're going to start chapter 3. We're actually putting 3.1 and 3.2 together. So we're talking about exponential and logistic functions. So what are exponential functions? Let's look at some examples. An exponential function would be if I have like 2 to the x power, say equals y. So what's different about this one versus the normal polynomial functions is that normally I have something x to an exponent. I can have an exponent of 2, an exponent of 3, an exponent of 4, so on and so forth. An exponential function has the variable in the exponent. That's the reason it's called exponential. So the first couple of problems ask you to identify what is and what is not an exponential. So we'll start off with this. These we'll call yes. They are exponential. Over here, no. So what is an exponential function? 3 to the x, negative 3 times 5 to the x plus 2. It's exponential. I could even do 1/2 to the x. Notice that each one of those has an exponent of x. What is not would be, say, x to the 5th, x to the 1/3, or even kind of a weird one, x to the x. Okay, for exponential, the base has to be a constant. So this one right here is a no, because the base is not a constant. So go ahead and pause the video now and try the first 6 problems, so 1 through 6, and all you're doing is saying yes or no, is it exponential, and if it's not, explain why. So for all 3 of these, this one, and this one, the reason why they were not is because the base was not a constant, and then for this one and this one, the exponent was not a variable. So there's my reason for those 3. Alright, so the next thing we need to talk about, 0, negative, and fraction exponents. And you've actually already seen this, what this means, but if I have 2 to the negative 1, that just means I do the reciprocal. If I do 2 to the negative 3, I still do the reciprocal, and that exponent of 3 stays on it. So I'd get 1/8. That's what negative exponents mean. If I get a fraction exponent, say I have 4 to the 1/2, well, that just means the square root, because the bottom number is the root, of 4 to the first power, which is 2. Likewise, what if I have 8 to the 2/3? Well, that's the cubed root of 8 squared. I'd say, well, the cubed root of 8 is 2 times 2 times 2, so that's the same thing as 2 squared, which would be 4. Also, if I have 2 to the 0 power, 8 to the 0 power, or even 100 to the 0 power, it doesn't matter, it's just 1. Anything to the 0 power is 1. So if I look at the problems on your page, see if I can scroll down here. Right here. There we go. I'm going to pick one of these to do real quick. We'll look at number 8. So number 8 says I do 6 times 3, and then I'm substituting this in for x. So negative 2. Well, that negative tells me I do a reciprocal, so this is going to be 6 times 1 over 3, and since I did a reciprocal, it's now a positive 2. And then that 3 squared is 9, so this becomes 6 times 1 over 9. Well, I know 6 is the same thing as 6 over 1, so if I multiply those together, I get 6 over 9, and if I divide both by 3, I get 2/3. That's my final answer. For these problems, if you end up with, say, a square root, just leave it square root, because it tells me to do the exact value without using a calculator. So it's okay to leave an answer like that if it happens. Okay, so leave your answer exact. We're not getting decimal answers here. And so that's what you need to do that next section, 7 through 10. Alright, transformations. So those transformation rules that have been on our test for the last 2 chapters are not going away. Sorry. They're going to look really exactly the same. So let's take a look at this. Let's say I have 2 to the x. If I want to shift this up 3, it becomes 2 to the x plus 3. If I want to shift it right, we'll say 2, then it becomes 2, and then remember left and right is inside where the x is, so it's going to be x minus 2, because we know left and right are backwards. Let's say I want to shift it left 3 and down 4. Okay. Well, this would be 2 to the x, so I'm shifting it left plus 3, and then down 4 minus 4. Okay, let's say instead of 2 we use e. And we've talked about e before. I believe it's been a while. If not, we'll talk about it again when I get back. But e is just a number. We know that pi is 3.141592653 E is just a number, just like pi's a number. It is 2.7182261826 ... And I tried doing this from memory, so I may have made a mistake in there. But anyway, e is just a number. It's 2.7 ... It keeps going forever, just like pi is a number. So when I see e, just think that, 2.7. So occasionally we'll see something that looks like this, e to the x. Okay, again, e is just a constant, so this is still exponential. Well, let's say I want to reflect this about the x-axis. Well, if I reflect it about the x-axis, that means the negative goes outside. So it would look like that. If I wanted to reflect it about the y-axis, then it's going to be e to the, and I put the negative with the x, so negative x. Well, let's say we're going to do some stretching and compressing. Well, let's say I have a, spell that right, horizontal stretch by 3. Well, we know horizontal is inside where the x is, and it also I have to do a reciprocal. So this is going to be e to the 1/3 x. Well, what about a vertical stretch by 3. Well, vertical's on the outside, so this would be 3 times e to the x. And a lot of times we'll put it in parentheses to show that that x is just on the e. And then what if I do it backwards? What if we do something like we'll do 3 to the 5 minus 4x plus 2. Alright, and I ask you, well, what are the transformations? Now, I'm not going to write them out because, as you can tell, the handwriting is worse than normal. It's because I'm doing this with a stylus, and it's kind of hard to write with it. So I'm going to actually say these out rather than actually trying to write them out. So this one right here is a vertical stretch by 3. This one tells me I'm going up by 2. This 5 right here by itself tells me I am, because it's added to the x, tells me that I am going left 5 units. The fact that there is a negative in front of the x tells me that I am reflecting about the y-axis. And this 4 right here that's multiplied to the x tells me there is a horizontal compression by 1/4, because I had to do the reciprocal. So I can look at this and come up with my transformations. Again, the rules all work exactly the same way. They might look a little different, but they still work exactly the same way. So now, look at problems 15 through 24. 15 through 24. And knock all those out. And then pause the video here, and then push play when you're ready to move on. Alright, so it says creating exponential functions. So first thing we're going to do is look at the two tables. So we're going to look at problems 19, 20, and then 11 and 12. And I know that seems weird because we had they're out of order, and that's okay. Specifically, I'm going to look at problem, actually I'll make one. Let's say we have x values -2, -1, 0, 1, and 2. Some y values. And we got 2. Yeah, I think that's right. So, if I want to look at this and come up with my rule, I start off by finding the x value of 0. Now this is telling me it's exponential, and I know that this is going to be in a form that looks like this. A times b to the x actually, yep, just like that. Yep. I know it's going to look like this. When I plug 0 in for x, it doesn't matter what I plug in for b, this entire thing is going to become 1. So the fact that I have a 2 right here instead of a 1 tells me that I am multiplying 1 by a number and getting 2. So this number right here, so when x is 0, whatever that number is my a. So I know that this is 2 times something to the x power. Now exponential functions have a pattern to them, and I'm always multiplying. So I'm just going to pick any 2 numbers on my y side, any 2 of these consecutive numbers, and divide them. So for instance, I'll take 8 divided by 4. Well, 8 divided by 4 is 2. And I didn't have to use that one. I could have said, well, let's do 2 divided by 1. I'd still get 2. I could have said 1 divided by 1/2. It doesn't matter which number I picked. So pick a number, divide it by the previous number, and that gives me the what's inside. And so that would be my rule. Well, let's see how that looks on your paper. So if I scroll down to this one right here, oops. Alright. So I'm going to look at this one right here, which is actually number 19. So I know it's going to be in the form y equals a times b to the x. So we're going to say, okay, I first see, well, x equals 0 right there. Well, when x equals 0, my function is 2.3. Well, that gives me the a. So a is 2.3. Next, I find the b. I just take any number and divide it by the previous one. So if I erase this right here, pull my calculator out. If it works, it might actually not. Go for my other calculator. Okay, so I'm going to pick two numbers. Doesn't really matter which two numbers. I'll go with these two. I'm going to type in the second one, which is 2.875 divided by the previous one, 2.3. And I get 1.25, which is my B, 1.25. And that is my exponential equation or function. Alright, so you're going to do the same thing on problem 20, and then at the top right hand corner, problems 11 and 12. Alright, so then we're going to move on to the section that's 1 through 6. It says, tell whether the function is exponential growth or exponential decay. So to do this, I'm going to show you some examples. So growth, decay. Let's say I have 3 to the x, 5 to the x, e to the x, 1/2 times 4 to the x. Okay, all of these are examples of growth. All of these are example of decay, and if I put some number in front of that one, yeah, it's still all decay. So to tell the difference, you look at which number is being hit by the exponent. Well, notice that in this example and in this example, I gave you two different numbers. That number in front, in this case the 3 and the 1/2, are distractors. They do not tell me anything about growth or decay. I just look at the number being hit by the exponent. For growth, the number being hit by the exponent is going to be greater than 1. For decay, the number being hit by the exponent is going to be less than 1. Okay? So this number is less than 1, that number is less than 1, that number, they're all less than 1. Now it's really easy to think, oh, so if it's a fraction, it's decay, if it's a whole number, it's growth. Well, the problem with that is, what if I give you this problem? We'll say 3 over 2 to the x. Well, notice that 3 over 2 is greater than 1, so that's still growth, even though it's a fraction. So it's whether the base is less than 1, it's decay, greater than 1, growth. So if I get this out of my way, and if I scroll down, we're going to look at 1 through 6. So cooperate with me. There we go. So I'm going to pick one of these real quick to look at. We'll look at number 4. So number 4, I see that number right there is a lot more than 1, but that number doesn't matter. I'm only looking at the number that's being hit by the exponent. The number being hit by the exponent is less than 1, so that means this one right here is exponential. Oh, let me spell. Decay. This one is exponential decay. Alright, so go ahead and try those other problems in that section, and then we'll move on to the next one. Alright, so to move on to this next section, they give you an initial value, I'm going to call my initial value my A, and then they give me a rate. We're going to call our rate B. And we're calling them A and B because it's going to look just like what we saw earlier. Okay, so my initial value is going to go here. My rate is going to go here. We'll do an example. Let's say I have an initial value and my rate, and I say I am increasing by 12%. Now I have to be very careful when I say I'm increasing by 12%, because if I say that my rate is just 0.12, well, that's not an increase, that's a decrease. Okay, so if I want to increase by 12%, I start off with 1 and then add my 0.12, because my percentage changed to a decimal 12. So increasing by 12% really means I'm at 1.12. That would be my rate, or the B. So for this problem, if I have an initial value of 12 and my rate is increasing by 12%, I would say y equals 12 times 1.12 to the x power. What if I have a initial value of 3.2 and my rate is decreasing by 22%. Well, if I'm decreasing, again, I'm not going to plug in just 0.22 because that actually gives me way more than a decrease of 22%. But because I'm decreasing, I'm still starting off at 1, but because I'm decreasing instead of increasing, I'm going to say minus 0. My rate. Well, 1 minus 0.22 is going to give me 0.78. And that's going to be our B, or our rate. So my equation here would be y equals 3.2 times our rate, 0.78, to the x. Notice that my value being hit by the exponent is less than 1, so this is exponential decay because it's decreasing. Alright, now go ahead and try numbers 7 through 14. So don't do 15 through 18 yet. Hold off on those. Just do 7 through 14 right now. The next video, the part 2 video, will tell you how to do these problems. And